Hello everyone, in this tutorial the capabilities of HyperMesh CFD software and AcuSolve solver will be presented in relation to CFD Underhood Thermal simulations. A simplified geometry of an internal combustion engine inside the canopy will be used for the CFD model as shown in the images. A fan with a shroud layout, rotated at 1500 RPM, generates a flow circulation inside the canopy and through the louvers. At the front and rear of the canopy there are two radiators used to cool the engine. As the air passes through them, heat is transferred from the hot engine coolant and air's temperature increases. Furthermore, high surface temperature is defined in specific areas of the engine like the exhaust manifold, the crankcase and the oil pan, contributing to the temperature field inside the canopy. The aim of this simulation is to solve the flow and temperature fields created by the interaction of the air with the fan, the radiators and the hot surface of the engine. The solution of the model will be done in two different parts. First, the simulation will be solved as a steady-state problem using the moving reference frame or MRF method without taking into account the transient phenomena caused by the fan rotation. Thus, the result will be the average flow and temperature fields in the equilibrium state of the system. In the second step, the results of the steady-state simulations are used as initial conditions in the transient problem, where the rotation of the fan blades will be modeled with the rotating mesh method. The two simplified bodies that make up the radiators of the system will be modeled using the heat exchanger component utility. The user can input information about the cooling properties, pressure drop and thermal performance of the radiator to achieve an accurate modeling without including the complexity of the individual system components. In addition, as part of the simplification of the model, the wrapping utility will be used for the engine parts. The wrap tool can create a watertight meshed model of the engine, merging its individual parts and minimizing the manual work needed to clean up its geometry. Now let's start with the setup of the state simulation, which will be split into four different sections. The geometry cleanup and surface meshing of the model's components will be demonstrated, followed by the physics definition and finally volume meshing. Firstly, I will proceed with the preparation of the canopy parts that will not be wrapped. I will start by loading the Parasolid CAD model by clicking on File, Open, and selecting it from the browser, or I can directly drag and drop it into the HyperMesh CFD modeling window. Our first target is to properly organize and simplify the different parts of the model to have a more efficient workflow later on. I'll click into the part browser and select the Collapse All option. Then I will expand the Underhood_AS assembly along with the parts and the engine, visualizing all the parts but without the individual solids under them. I will create three additional parts for the two heat exchangers and the moving reference frame solids and move the corresponding solids below them. Next, I will isolate the part assembly and go to Geometry ribbon, Edit Group and select the Combine command to merge all the individual solids together, aiming to simplify the canopy assembly. The Keep Common Interface option should not be enabled to produce a final single solid. After executing the command, the remaining solids will be transferred into a new part named Canopy Parts and the empty parts assembly will be deleted. Next, I will isolate the large heat exchanger along with the canopy shell solids and apply the Combine command, this time with the Keep Common Interface option checked. By doing this, the two solids will be connected together but not merged. The shared faces can be visualized with yellow color by enabling the topology view under the visualization toolbar. To further minimize the number of the model solids, I will proceed by combining the oil and fuel tanks with the rest of the canopy. By creating a section cut at the XY plane, we can notice that there is a very small gap between the tanks and the canopy walls, which can also lead to bad quality volume elements. In order to seal it, I will use the Move tool under the Home group. Firstly, I will set the selection filter to solids and pick both tanks. I will click on the up arrow in order to restrict the movement only along the Z-axis and then select one of the bottom edges of the tanks and snap it to an edge of the canopy bottom surface. Next, the process will be repeated for the side gaps, this time individually for every solid. And now the three parts can be successfully merged. After completing the editing of the canopy, the creation of the moving reference frame volume comes next. I'll start by setting the MRF part as current and hide some surfaces of the canopy to reveal the shroud area. With the command solids under the create group, I will create a cylinder by snapping its center to the rotational axis of the fan and define a radius of 0.5375 meters and a length of 0.226 meters. Next, I will adjust the position of the cylinder along the y-axis using the move tool and snap its right edge to the outer edge of the shroud. In this way, the MRF disc encloses symmetrically the geometry of the fan, and its edges are positioned in the middle of the blade's tips and the surrounding shroud surfaces. Finally, I will boolean the fan and the MRF disc solids to create a common interface between them. Closing the geometry preparation chapter of the non-wrapped parts of the model, we have to design the flow domain around the geometry. After adding the corresponding part named as domain under the part browser, I'll use the box command under the create group, and I'll click on the box option and define the dimensions of the domain. With the move tool in the micro dialog, I will correctly place the domain relative to the canopy. To complete the process, I will create common interfaces between all the non-engine parts and the domain using the combine command again. Following the modification of non-wrapped parts, their surfaces should be checked for any possible errors with the corresponding command under the repair group. We can observe that there are some self-intersections which are located at the blades of the fan. I'll select the split surface method to fix them with a curvature of 0.5. Now the surfaces are ready to be meshed. I will start by defining some surface mesh controls for the different areas of the model, as some of them require higher resolution accuracy. The finest average element size will be used on the fan surfaces to properly capture the complex local flow field generated by its rotation. It will be set to 5 mm with a geometric feature angle of 10 degrees to increase the mesh density and the highly curved blade tips. A second mesh control will be defined for the MRF disc, the two heat exchangers, and the inner shroud surfaces with an average element size of 1 cm. Finally, the rest of the canopy surfaces will be selected and set a mesh refinement of 2 cm. Now, after making sure that everything is visible except the engine parts, all the surfaces will be box selected to be meshed. The average element size will be defined at the window of the surface mesh command and will be set to 0.4 meters. This value is generally referred for all the surfaces which either do not have any applied mesh controls or their defined element size is larger than 0.4 meters. In that case, this size will only be applied to the surface of the domain. After the completion of the surface meshing, we can visually inspect the meshed surfaces. Now it's time to jump to the next chapter of the model setup, which refers to the preparation of the engine parts. The objective is the same as in the previous section, the production of a surface mesh. However, due to the increased complexity of the engine parts, we will follow a totally different procedure. As we mentioned during the introductory part of the video, the wrapping utility will be used, which significantly simplifies the process and minimizes the user input regarding both geometric lap and meshing. To initiate the wrapping process, I will quickly remove the bolts of the engine. This can be done in two ways for that specific model. The easier one is to simply select the bolt parts from the part browser and delete them. However, this may not be applicable in models with a very high count of parts or with non-well-organized part assemblies. The second way is to take advantage of the selection tools. I will firstly set the entity selector to solids, select the three different types of bolts, and then by right-clicking on the modeling window, I will navigate to the Select, and similar command. In that way, all the bolts of the engine will be automatically highlighted and can be isolated and deleted. The next step is to convert the CAD model of the engine into a tessellated geometry, as it is the required input for the wrapper. Under the Home group, I will select the Convert command and set the Convert option to FE geometry. The surface meshing method will be set as faceting and the size definition to fine to achieve an accurate representation of all the geometrical features. After the generation of the facets, we can use some of the highly automated tools to apply some further simplifications to the geometry. I'll switch to the discrete ribbon and under the Edit group, I'll select the Cap Holes command. In the guide bar, the selector should be set to parts and all the visible parts will be selected. Next, I'll enter a maximum width of 0.1 meters, which is quite large value, aiming to pass all the open holes of the model. After clicking Cap, we can observe at the bottom left side of the screen the number of holes that were filled. Now I will continue using the Cap Holes command in a more manual manner to further simplify some parts of the tessellated engine. Firstly, I'll change the selector to nodes and select the 4 nodes at the edges of the intercooler part. We can see how the tool managed to fill the small cavities and generate a simplified flat surface instead. Then I'll isolate the engine cover and the engine cable parts and set the selector again to surfaces. I will manually select the surface of spark plugs ports which were not recognized during the automated cap process to patch them. After closing all the small holes, which can lead to a poor quality wrapped surface, we are ready to apply the wrapping of the engine. Clicking on the Edit tool, I select the Adaptive Wrap method. I will select all the visible parts in the modeling window and define the wrap parameters. The wrapping method will be set to Type Wrap to capture with high accuracy all the complex geometrical features of the engine, and the wrapping type to Exterior as we want to generate a single external surface out of all the different engine parts. Finally, the average element size will be set to 0.02 meters and the feature angle to 10 degrees, producing a fine enough mesh. After wrapping, all input parts to wrapper are removed and a new part called CFD Wrap 1 is created. I will right-click on the generated solid and rename it as Wrapped Engine. Now I can delete all the empty parts of the previous assembly and have a clean and well-organized part browser. The next step is to convert the surface mesh produced by the wrapper into triangular elements. For that reason, I'll use the remesh command under the Mesh Update group. After selecting all the visible surfaces, I will set the meshing parameters similar to those used for wrapping. At this point, we should highlight that reviewing the remeshed surfaces is necessary to assess the mesh quality, spot problematic regions, and redo the surface mesh if required. Moreover, under the Mesh Update ribbon, there are several tools that can be used to further improve the mesh quality in areas specified by the user. Finally, we need to apply a surface mesh quality check by using the Repair command under the Quality group. From the first drop-down menu on the guide bar, I'll check the number of duplicates, intersections, and free edges. In this case, a small number of intersections will appear. I will keep the repair method to autofix and click Fix All. It is likely that the process will need to be repeated for 2 or 3 times to completely eliminate all intersections. In case any intersection remain, the repair method remesh elements can also be applied by setting a smaller element size. The preparation of the engine will be completed in the same way as we did before, by using the Combine command and creating common interfaces between the fluid domain and the wrapped geometry. At this point, all the model surfaces are meshed, and before generating the volume mesh, we'll proceed by setting the physics of the simulation. Initially, I will switch to the flow ribbon and click on the physics command under the setup group to define the simulation parameters and solver settings. Under the physics model settings, I will verify that the flow is set as single phase and incompressible. Next, I will set the time marching to steady and select the Spaller-Talmaros turbulence model, as it's a very robust choice for simulations of steady-state flows. Finally, the pressure scale will be set to relative and the heat transfer option will be checked. Switching to solver controls, I will set the relaxation factor to 0.5 to ensure the stability of the simulation, the maximum steps to 100, and make sure that the flow, temperature, and turbulence equations are enabled. Having completed the basic simulation parameter setup, the definition of the reference frame rotation follows. I will isolate the MRF disk we created previously, and under the domain group, I will select the reference frame command. After selecting the solid displayed in the modeling window, I will define the axis of rotation by using the surface center as a snapping point. By clicking the Y button in the micro dialog, I will make sure that the rotation axis is properly aligned, and next I will click the plus-minus button to flip the rotation direction in the negative Y axis. Finally, the angular velocity of 1500 rpm will be converted into the value of 157.08 radians per second and will be entered in the corresponding text field. Before clicking the tick mark button to apply the command, we need to make sure that the Include Bounding Surfaces checkbox is selected. At this point of the setup of the steady-state simulation, it is also necessary to activate the controls for the rotating mesh motion and then set a rotational speed of 0. This will allow the restart procedure to be applied and start the transient simulation using as initial conditions the last time step of the steady-state run. To do so, I will switch to the motion ribbon, which includes commands related to mesh motion, and under the direct group, I will select the rotation command. The same procedure with the MRF definition will be followed to activate the zero velocity rotating mesh motion. Finally, I will click on the settings command under the setup group, set the mesh motion to specified, and after switching to the solver controls tab, I'll uncheck the mesh deformation option. The next entities of the model that require a specific modeling technique are the heat exchangers. Switching back to the flow ribbon under the domain group, the heat exchanger command can be found. I will start by selecting the large heat exchanger solid and then define its surface whose normal faces the outside of the equipment as the inlet. Next, in the setting tab, the thickness of the rectangle will be defined along with the coolant heat reject and the coolant flow rate. Now I will move to the friction tab to input the correlation of the friction factor and axial velocity as a piecewise linear function. The Darcy friction coefficient is used to model the flow restriction by the heat exchanger, and experimental data in the form of pressure drop versus velocity can be used for its determination. Furthermore, the transverse friction factor will be set to 50, which is the percentage of the friction coefficient applied perpendicular to the axis of the main flow. Finally, the effectiveness of the heat exchanger will be set as a constant with a value of 0.95. Now the same procedure will be followed to set up the characteristics of the small heat exchanger. After completing the setup of the heat exchangers, I will create and assign the material properties. Under the Setup group, I will open the Materials library, switch to My Materials list, set the settings to Fluid, and press on the plus icon. A new fluid material will appear on the list, and after naming it as air_40 degrees, I will assign to it the properties of air at 40 degrees Celsius. Right next to the material library icon, the material command is located, with which I will select all the solid parts of the model and assign to them the material we previously created. In this point, we should highlight that all the solid parts except the heat exchangers, which are modeled as fluid domains, will be deleted at the later stage, as we are only interested in simulating the flow and temperature fields inside the canopy. Now we will proceed to the most crucial part of the physics setup, which is the definition of the boundary conditions. A good set of boundary conditions will ensure the numerical stability of the simulation, along with the accurate modeling of the phenomenon. I will start by selecting the command constant under the boundaries group to set an inlet velocity of 0.3 meters per second, normal to the inlet phase, with a uniform distribution. In reality, the creation of the flow field is exclusively due to the rotation of the fan, with the ambient air around the geometry being static. However, this would create large swirls within the domain and consequently reverse the flow on the inlet and outlet faces, causing instability in the simulation. For this reason, we define a small inlet velocity to impart a predominant direction to the flow, avoiding the flow reversal with minimizing the disruption of the flow phenomena near the canopy. Next, I will select the outlet of the domain, setting a zero static pressure. Furthermore, I will enable the backflow conditions option and set the eddy viscosity and temperature backflow type to exiting area average. The side and top surfaces of the domain will be assigned as slip walls to avoid solid and fluid interaction, and on the other hand, the grout will be defined as a non-slip wall while leaving all the available options as default. Finally, I'll use again the no-slip command to define temperature values at the surfaces of the engine's hot parts. By clicking on the three dots next to the entity selector in the microbar, I will set the advanced selection by group. I will pick the engine exhaust surface group from the list, isolate it, and select all its surfaces. Next, I will set the thermal boundary condition to temperature, set the value to 500 Kelvin, and click on the play button to apply the changes. The same procedure will be repeated for the engine block and the engine pan by setting their surface temperature to 400 and 350 Kelvin respectively. After successfully defining all the required physics parameters, we will move to the final chapter of the steady-state simulation setup, which is the volume meshing and the execution of the simulation. The first thing we need to do is define the controls of the boundary layer meshing. Firstly, I will isolate the fan solid along with the four cylindrical shroud surfaces around it. Considering that in this region the most intense flow phenomena will occur, due to the fan rotation, we want to have an increased mesh refinement near the walls. Switching back to mesh ribbon under the mesh controls group, I will select the boundary layer command and box select all the visible faces. The first layer thickness definition will be set to constant, with the first element height of 0.6 mm and 7 layers in total with a growth rate of 1.3. The termination policy will also be set to squeeze. Now, I will select the shroud faces, and by using the select adjacent utility 2 times, I will make the connected curved surfaces appear. Next, I will select them and define another boundary layer mesh control with the first layer height of 1 mm this time, while keeping the rest of parameters as before. A final boundary layer mesh control will be defined for the rest of the canopy parts. By isolating the canopy parts from the part browser and hide the previously defined controls, we can select the rest of the surfaces. The first layer height will be set to 2.5 mm and the number of layers to 5 with a growth rate of 1.2. To wrap up the volume meshing chapter, we will also need to define some refinement regions for the tetra-element mesh core. I will start by applying a volume mesh control to the MRF disk and the 2 heat exchanger solids with an average element size of 0.01 meters. At this point of the pre-processing phase, we will delete the solid parts, which will not be included in the simulation. The reason why we kept them until now was the easier manipulation of their surfaces for defining the mesh controls along with the boundary conditions. If we deleted them earlier, we had to manually hide all domain surfaces to reveal them each time, making the process slower and less efficient. To ensure that the removal process was done correctly, I will use the fixed database utility by right-clicking on the model at the top of the part browser and then delete the remaining empty parts. The last step is to create some refinement regions around the canopy to achieve a high density mesh inside of it and a smooth size transition to the larger elements of the far-field domain. From the zones command, I'll select the box mesh zone option and I will click on the box button in the guide bar, leaving the dimensions as default. The average element size will be set to 0.02 meters. Next, I will click the play button and press again on the box option to create a second refinement box and set the dimensions as shown. The average element size will be set to 0.08 meters. As the second box intersects with the ground face, we should remesh it to ensure that this control is also applied to the surface and refines it accordingly. The average element size will be set to 0.4 meters as it was previously. After defining all the necessary controls, we need to validate the model before proceeding to the generation of the volume mesh. Switching back to the geometry ribbon, under the repair group, I will click on the validate command to check for any remaining errors. If everything is done correctly until now, only sliver surfaces will appear, which can be removed by reducing the default tolerance. Now we are ready to produce the volume mesh for the model, selecting an average element size of 0.4 meters. The retain existing surface mesh option should also be enabled, since the surface mesh is already created. When this process is completed, we can visually inspect the results by using the section cut tool. Now the final step is to execute the steady-state simulation. Going to the solution ribbon under the simulation group, I will click on the run command. On the window that appears, I can change the name of the problem and define a specific problem directory where all the simulation files will be saved. Furthermore, depending on the available computational power, I can select to run the simulation in a serial or parallel mode and define the corresponding parameters like the number of cores. Next, I will deactivate the automatically defined pressure reference option, and by expanding the default initial conditions list, I will set the temperature to 293.16 Kelvin. Finally, by clicking on the Run button, the solution will start. In case we want to run the simulation in a remote system, the export option can be used. It will generate the mesh.dir folder, including mesh information in the form of binary files, the .imp text file, where all the parameters and settings of the simulation are written, along with the AcuSim.cnf file, where the name of the simulation is mentioned. Having completed the setup and execution of the steady-state simulation, we will now proceed to the second main section of the workshop. The preparation of the transient simulation will be demonstrated, where the rotation of the fan will be modeled through time using the rotating mesh method. This chapter will be much shorter, as only certain parameters of the model's physics will change, while the geometry and mesh remain the same. Using the previous model, I will go back to the physics setup to switch the simulation type from steady-state to transient by adjusting the corresponding parameters. The time marching will be set to transient, and two new options will appear regarding time step size and total simulation time. The time step will be defined as the time required to perform 3 degrees of fan rotation. This is a solid option as it ensures sufficient accuracy in capturing transient phenomena while keeping computational demands and results data volume at acceptable levels. Furthermore, it guarantees the numerical stability of the solution algorithm. In order to convert the degrees of fan rotation to a time interval, we will initially convert the angular velocity units from rounds per minute to degrees per second. Then, the delta t is calculated by dividing the blade rotation angle per time step with angular velocity, and its value is 0.33 milliseconds. The total duration of the transient simulation is determined as the time needed for 3 full fan rotations. This figure ensures a balance between computational efficiency and the comprehensive capture of the full development of flow phenomena induced by fan rotation. The total time is calculated as 0.12 seconds by dividing the 3 degrees of rotation by the angular velocity in degrees per second. Lastly, under the solver control settings, the minimum and maximum stagger iterations will be set to 2 and 6 respectively. Given that the existing steady-state model has been used to create the transient setup, it is only necessary to modify the solution parameters appropriately and active the mesh rotation. As presented previously in the section on the MRF model preparation, the parameters for the rotational mesh motion have already been defined, but with zero angular velocity. Thus, at this stage, the proper angular velocity value will be defined, and at the same time, the reference frame will be deactivated. Firstly, I will rename the MRF part under the part browser to rotating mesh. Next, I will switch to the setup browser, when I can either delete the defined reference frame or set the angular velocity back to zero. Finally, I will right-click on the rotational entity under the motion group to edit it and set the angular velocity to 157.08 radians per second. An optional step for the transient setup is to edit the results that will be extracted from the simulation. Moving to the solution ribbon, under the outputs group, the field command can be found, including information about the frequency and type of exported results. For the solution variables list, I will enable the write initial conditions options and set the output time interval to 3. Result states will be extracted at intervals of every 3 time steps, equivalent to a 9-degree rotation, providing adequate resolution to visualize the fan rotation and observe transient flow phenomena, while effectively reducing the size of the result files. To further minimize the size of the extracted result files, I will select from the settings list the derived, nodal residual, and time average variables and disable the writing of results. The second and final phase of the transient simulation preparation is the setup of the restart procedure. A set of well-defined initial conditions is required to ensure the stability and the reduction of computational time of the transient simulation. A common practice in problems involving mesh rotation is to use the steady-state MRF solution of the problem as initial conditions. Thus, the transient solver in the starting time steps of the solution resolves significantly smaller fluctuations or gradients of the flow field as it is in an already evolved state. Furthermore, in this case, the thermal field has also been established using the steady-state simulation, which often requires significantly longer physical time than the flow field. To activate the restart utility, I will open the AcuSolve launcher, expand the restart options list, and enable the restart from previous solution checkbox. After making sure that type is set to modified, I will click on the browse button next to the working directory option and select the AcuSim.dir folder of the steady-state simulation. The problem name will be then completed automatically. Finally, I will verify that the run number is set to last run and time step to last step, and enable the restart time step option. Now the simulation is ready to be submitted by clicking on the run button. When running simulations remotely on a computer array or a workstation, it is advisable to export the solver deck without including the restart procedure via the HyperMesh CFD graphical interface. This is because the directory of the steady-state solution is not located at the local machine. Thus, it cannot be defined properly. All the transient simulation parameters can be set using HyperMesh CFD as was demonstrated, and the solver deck will be exported. Then, in order to activate the restart procedure, the input file should be edited, adding the restart module manually as it would have been written by the graphical user interface. The text section shown is added at the end of the IMP file before the run command. This workshop has now come to its end, and in conclusion we will present some images and animations of the results. If you would like to learn more about the post-processing capabilities of HyperMesh CFD, you can refer to the video displayed on the screen, where a comprehensive analysis of all the post-processing commands is presented. Finally, you can find more detailed information and tutorials by accessing the Altair Online Help webpage. Hope you enjoyed this video and thank you very much for your time.